This is the fifth video in my series of videos on Georg Cantor's contributions to the founding of the theory of transfinite numbers. I'm going to get straight into things with this video, so no lengthy introductions or anything like that. We're really going to be kicking off with the definition of ordinal number, which is ordinal numbers are going to be the main focus now for the rest of the videos in this series. They're the main focus of the rest of Cantor's work in this particular article. So the ordinal type of a well-ordered aggregate is called an ordinal number. So remember, an ordinal type, this is a more general concept that's applied to simply ordered aggregates. So well-ordered aggregates being a particular type of simply ordered aggregate, ordinal numbers are just particular types of ordinal type. So in Cantor's work, this what I'm going to be going through at the start of this video is mostly from section 14 or chapter 14 in Cantor's work. So this theorem here I've actually kind of postponed from the previous section. It doesn't make any difference. I just felt that it was more appropriate to put it in this section here. But this is theorem N from section 13. So for well-ordered aggregates f and g, either f and g are similar to one another, or f is similar to a definite segment of g, or g is similar to a definite segment of f, and each case excludes the other two. So let's say, for instance, that our well-ordered aggregate f has an ordinal number alpha, and that g, again a well-ordered aggregate, has an ordinal number beta. So in this first case here, f and g are similar to one another, then it kind of makes sense. We've got an intuitive notion that they're kind of the same size, they're the same in many respects. Obviously this phrase similar, aggregates being similar, has got a very precise meaning, but even visually, intuitively, we feel that they're kind of the same size. So it makes sense for us to say here that alpha is equal to beta. Similarly, in the second case here, f is similar to a definite segment of g. A segment of g is kind of a particular type of part of g. So if f is similar to that part of g, then it kind of intuitively feels like f is going to be smaller than g. So therefore we say that alpha is less than beta. And unsurprisingly, in the last case, we say that beta is greater than alpha. Okay, so what this means is that we can actually put a simple ordering on well-ordered aggregates, or should I say on ordinal numbers. So if we've got an aggregate and the elements of that aggregate are ordinal numbers, then we can at least place a simple ordering. We can say, given any two ordinal numbers from this aggregate, two non-equal ordinal numbers, which is the greater and which is the lesser. Because this is a simple ordering, then unsurprisingly we get the transitivity. So alpha is less than beta and beta is less than alpha, gives that alpha is less than gamma. So that's not really too much of a surprise. But now that we've got the ordering out of the way, that's really all there is to it. We can start to move on now to arithmetic of ordinal numbers, and this is going to be certainly the main focus now. So we're going to start off with just the simple arithmetical operations of addition and multiplication on ordinal numbers. Let's move on now to addition and multiplication of ordinal numbers. Obviously, with ordinal numbers being particular ordinal types, a particular variety of ordinal type, then really how we defined addition and multiplication for ordinal types carries straight over to ordinal numbers. But I'm just going to recap some of that stuff. There are a couple of new things that I need to add to that, particularly with regards to ordering, etc. So if f and g are well-ordered aggregates, let's assume that the ordinal number of f is alpha and the ordinal number of g is beta, then we can form the, provided that f and g don't have any common elements, then we can form the union aggregate of f and g, which will, by theorem, I think 12.e, which I definitely mentioned in my previous video, but I don't think I proved it, the union aggregate will itself be a well-ordered aggregate. So we can define alpha plus beta to be equal to the ordinal number of the union aggregate. So in general, if we were just dealing with ordinal types, or we didn't know that this was a well-ordered aggregate, we could still find alpha plus beta, but we wouldn't be able to refer to it as an ordinal number, it'd just be an ordinal type. But because we know that this is going to be a well-ordered aggregate itself, then alpha plus beta must be an ordinal number. So we've got a kind of closure under addition, at least, when it with respect to ordinal numbers. Adds two ordinal numbers together, we get a third ordinal number. It doesn't kind of break out into the other ordinal types along the way. And then it's easy to see that f is a segment of, or f is a segment, or f is at least similar to a segment of the union aggregate fg. So thinking back to what I was saying a couple of minutes ago, if the ordinal type, the ordinal number even of f is alpha, and f is similar or is possibly even equal to a segment of the union aggregate fg, then that means that since the ordinal number of this is alpha plus beta, in general we get that alpha is going to be less than alpha plus beta. Now the next thing here rests on this theorem. So this is theorem 30, so this is another theorem that I've just postponed from the previous section. So theorem 13.0, if a part f1 of a well-ordered aggregate f is not similar to any segment of f, then it's similar to f itself. So g is a part of fg, or is at least similar to a part of the union aggregate of f and g. It may or may not be, presumably it's not a segment, because we don't really deal with empty aggregates. Certainly if f was an empty, well, maybe not certainly, I don't know actually, if f was an empty aggregate, would it be considered as a well-ordered aggregate? I don't think so, because it wouldn't have a least element. So we can't really say that g is going to be a segment of fg. Whether it's going to be similar to a segment of the union aggregate fg, we don't know. Possibly we'll leave that possibility open, but it might be that g is actually similar to the whole of the union aggregate fg, and that's determined by this theorem here, 13.0. So we can't simply say that beta is going to be less than alpha plus beta. We can't guarantee that. We can only guarantee that beta is going to be less than or equal to alpha plus beta. So this is in quite sharp contrast to how normal numbers work. So if we've got two positive numbers, a and b, add them together, then the sum of those two numbers is going to be greater than either of the numbers taken individually. But that's not the case here. Now, it might be actually that it is the case, particularly if we're dealing with finite ordinal numbers, but once we get onto transfinite ordinal numbers, it's a completely different situation. We're getting all sorts of different behaviours coming up. The associative law for addition holds for ordinal numbers, and we've also got this kind of cancellation law. So if alpha plus beta equals alpha plus gamma, then we can say that beta equals gamma at least, but it doesn't work the other way round. So this cancellation law only works in this form. So if we had beta plus alpha equals gamma plus alpha, we wouldn't be able to conclude that beta equals gamma, for instance. And as with ordinal types, remember these ordinal numbers, they're particular ordinal types. With ordinal types, addition of ordinal types is not commutative, so alpha plus beta is in general not equal to beta plus alpha, and nothing changes there with ordinal numbers, so the commutative property doesn't hold in general. It might hold in particular instances, but in general it doesn't hold. So that's addition of ordinal numbers. Let's have a quick look now at multiplication. So if we've got our well-ordered aggregate G, its elements are lowercase g. If to each element of G we assign a well-ordered aggregate f sub G, such that f sub G is similar to f for each G, and that there's no common elements with any of the fg's, then putting all of these together, effectively replacing each G with its the aggregate that we've assigned to it to form this new aggregate H, then again theorem 12.e says that if we define it in the right way, that this can be considered as a well-ordered aggregate as well. So if it's a well-ordered aggregate, it's got an ordinal number, and the ordinal number we define as being alpha dot beta. So again, we've got a kind of closure under multiplication. Multiply two ordinal numbers together, we get another ordinal number, and we don't seem to break out of that particular subsystem of ordinal numbers. Associative law holds for multiplication. Distributivity holds, but only in this form. So we've got alpha dot beta plus gamma equals alpha dot beta plus alpha dot gamma. So we wouldn't be able to say, for example, that beta plus gamma dot alpha is equal to beta dot alpha plus gamma dot alpha. So these two would not be equal. We don't have I don't know, maybe you could call this left distributivity, something like that, but we don't have right distributivity. We've got another cancellation law. So if alpha dot beta is equal to alpha dot gamma, then beta is going to be equal to gamma. Again, it doesn't work the other way round. So beta dot alpha equals gamma dot alpha doesn't mean that beta equals gamma in that case. And we've also got a multiplicative identity. We didn't have an additive identity. So this comes back to the question about whether we consider the empty aggregate, if it exists, or any empty aggregates that may exist. Whether we consider them as well-ordered aggregates, my guess is not. Cantor doesn't explicitly mention them in his works, but I'm guessing that we don't consider them as well-ordered aggregates themselves. But we do have a multiplicative identity. And it's fairly easy to deduce that this is the case. That alpha dot 1, alpha times 1 is equal to 1 times alpha is equal to alpha. Not too difficult to see that. And again, we just like we had these inequalities here with regards addition, we've got some similar inequalities regarding multiplication. So if we consider alpha dot beta, and we make the assumption that beta is greater than 1, then we can say that alpha dot beta is going to be greater than alpha. But in general, irrespective of the value of beta, we can only say that alpha dot beta is going to be greater than or equal to beta, irrespective really of the value of beta. So that gives a bit of a rundown of addition and multiplication. So there's quite a lot of similarities there between this and multiplication, addition and multiplication of ordinal types, except we've got these new inequalities coming up. So we're going to develop some more properties now, arithmetical properties of ordinal numbers. Okay, so let's make a little bit of sense now of the operation of subtraction in relation to ordinal numbers. So if the ordinal number alpha is less than the ordinal number beta, there is a unique sigma which solves the equation beta equals alpha plus sigma, and this sigma is denoted by beta minus alpha. So in particular we get this beta equals alpha plus beta minus alpha. And I really want to emphasize at this stage that I can't just switch these around willy-nilly. Remember, we don't have commutativity in general when it comes to addition of ordinal numbers. So when we say that this sigma beta minus alpha is a solution to this equation, I couldn't say at the same time that it's a solution to beta equals sigma plus alpha. It doesn't work that way. So it's definitely beta equals alpha plus sigma, and that way round. Okay, and then we've got a couple of properties that we need to prove. Now, we've got to be careful here because it's very tempting to see these as just like the usual kind of relationships between expressions when we're dealing with ordinary numbers. So for example, here we might think about this as just expanding out the brackets. And similarly here, get rid of the brackets and we get something like gamma plus beta minus gamma minus alpha, cancel cancel equals beta minus alpha. But we've got to be conscious all the time of the fact that these things are very different. These ordinal numbers, they're very different objects. They are aggregates, they're not just numbers. They're actually aggregates, and we've got to discover these properties, and we do actually have to prove these properties. Sometimes as laborious as that actually is, we've just got to go through that process. So, okay, let's have a look at this one. We're going to prove this one first. So I'm going to start with the expression on the left-hand side. So this, using what we've got up here, then this is going to be the solution to the equation gamma plus beta equals gamma plus alpha plus gamma plus beta minus gamma plus alpha. So this is exactly what we've got written up here. And now I can use the associativity of ordinal numbers under addition to say that gamma plus beta is equal to gamma plus alpha plus gamma plus beta minus gamma plus alpha. And okay, now I can use the cancellation rule to get rid of these gammas here. So I can conclude that beta must be equal to alpha plus gamma plus beta minus gamma plus alpha. And then this equation is effectively what we've got here. Beta equals alpha plus sigma. So this is my sigma. But I know that sigma is represented by beta minus alpha. And I know that such a sigma is unique. It's a unique sigma. So if sigma can be represented by this symbol and sigma can be represented by this symbol, the only conclusion is that gamma plus beta minus gamma plus alpha is equal to beta minus alpha, which proves the first relationship here. Moving over here, so if we have a look at the expression gamma alpha plus gamma beta minus alpha, then using distributivity, remember it's kind of left distributivity that we've got with these ordinal numbers, then I can say that this is equal to gamma alpha plus beta minus alpha. But I know that alpha plus beta minus alpha is equal to beta. That's why I wrote that up there. So this is just going to be equal to gamma beta. So what I end up with is that gamma beta is equal to gamma alpha plus gamma beta minus alpha. Again, I get an equation that's of this form. Okay. So what I can say is that if this is effectively sigma here, but according to this, the solution to gamma beta equals gamma alpha plus sigma would be sigma equals gamma beta minus gamma alpha. So if I know that sigma can be represented again by this symbol and sigma can be represented by this symbol, the only conclusion is that gamma beta minus alpha is equal to gamma beta minus gamma alpha, which is what I needed to prove up there. Okay, so far we've looked at what happens when we do arithmetic with a finite number of ordinal numbers. Let's have a look what happens now when we go to an infinite number of ordinal numbers. So let's have a look now at what happens when we start to find sums of an infinite number of ordinal numbers. So if we've got a simply infinite series of ordinal numbers, beta 1, beta 2, beta nu, etc. So that means that there's the aggregate of these would be a simply ordered aggregate, so there's a definite order to them. They're not necessarily in order of magnitude, but there's some ordering placed on them, some simple order. Then if we define an aggregate, or we find an aggregate, G nu, that has a well-ordered aggregate that has the ordinal number beta nu for each nu, then we can form the union aggregate G of all of these G nus. And by theorem 12e, this is going to be itself a well-ordered aggregate, so it's got an ordinal type and even an ordinal number. And the ordinal number is represented by the sum of the individual ordinal numbers. So beta 1 plus beta 2 plus beta whatever. And we get just a single definite ordinal number beta, which represents the ordinal type, the ordinal number, of this well-ordered aggregate here. So now we're going to define alpha nu to be the sum from beta 1 to beta nu. Then this is obviously the ordinal number of the union aggregate of G1 to G nu. Okay. Not only that, G1 to G nu is a segment, with it being a well-ordered aggregate. It's a segment of the well-ordered aggregate G1 to G nu plus 1. So therefore we can conclude that alpha nu is less than alpha nu plus 1 for each nu, for each ordinal number nu. So we get an increasing sequence, infinite increasing sequence of these alphas, alpha 1, alpha 2, alpha nu, etc. And this is what's called a fundamental series of ordinal numbers. So what we see here then is that for every infinite simply ordered series of ordinal numbers, we can actually derive a fundamental series. So it's fundamental series because it's strictly increased. So it's infinite, but the terms are strictly increasing. So through this we can see that alpha 2 is going to be greater than alpha 1, alpha 3 is going to be greater than alpha 2. So what we're interested in now is investigating the behaviour of this sum through this. So from this point forward, really, if we're to consider an infinite sum of ordinal numbers, there's got to be a definite order to them. So compare this with infinite sums of real numbers, for example. We've got different behaviours depending on whether the series is absolutely convergent or not. In the case of a series that's an infinite series that's not absolutely convergent, then changing the order of the terms is going to change the overall sum. So we get a similar behaviour potentially here. So we definitely need to make sure that we do have a definite order placed on these. But provided that we've got this simply ordered infinite sequence of ordinal numbers, and we know that definite order, then we can effectively jump straight to, it will generate a fundamental series of ordinal numbers, and we can effectively jump straight to that. We don't need to deal with the betas, what corresponds to the betas. We can go straight to the fundamental series that's generated by it. Okay, so we're going to need to pay attention to this thing later on. Okay, so this aggregate here, this union aggregate G1 to G nu, is a segment of G for every nu. and the order number of G1 to G nu is alpha nu, and the order number of G is beta. So we can see then that alpha nu is going to be less than beta for every nu. So this gives us kind of an upper bound for the values that these ordinal numbers, this fundamental series of ordinal numbers, we found another ordinal number that kind of bounds those ordinal numbers. That series of ordinal numbers, they can't exceed this particular value. So what we're going to show now is that actually this is not only an upper bound, but it's effectively some kind of least upper bound. That if we were to choose a beta prime less than beta, there is going to be a point along this series of terms where alpha nu is going to be greater than beta primed for all terms following that particular term as well. So, okay, beta prime is less than beta. That means that because this is effectively the ordinal number of G, there must be a segment of G, B primed, that has the ordinal number beta primed. Okay, so if you remember, the segments of well-ordered aggregates can be defined by particular terms. We choose a particular term from our aggregate, well-ordered aggregate, take all of the terms that precede that term, and all of those terms form a segment, what we call a segment of a well-ordered aggregate. So let's say that F defines the segment B primed. And let's also say that F belongs to G nu naught. Okay, so in that case then, if we consider the aggregate G1, G2, G nu naught, then B primed is going to be a segment of this. It's going to be a segment of this well-ordered aggregate. It can be considered as a segment of this well-ordered aggregate, and therefore beta primed is going to be less than whatever the ordinal number of this well-ordered aggregate is, which is alpha nu naught. But this is a segment of the union aggregate G1 to G nu naught plus 1, which has ordinal number alpha nu naught plus 1, and that in turn is a segment of the next one along, the next one along. So we get that beta primed is actually going to be less than alpha nu for all nu greater than or equal to nu naught. So no matter which ordinal number we choose, beta prime, which is less than beta, that number will always be exceeded by some alpha nu naught, and indeed all alpha nu with an index greater than nu naught. Okay, so just coming back to all of this stuff here now, we can see that, for example, alpha nu plus 1 is equal to alpha nu plus beta nu plus 1. So alpha nu is just this, add beta nu plus 1 onto that, I get alpha nu plus 1. And I know that alpha nu plus 1 is greater than alpha nu, and therefore I can kind of rearrange this, thinking about what I did earlier in the video, solutions to equations, as it were. Then I can say here that beta nu plus 1 is equal to alpha nu plus 1 minus alpha nu. And I'm also going to define beta 1 to be equal to alpha 1. Okay, so now starting with this, alpha nu is equal to beta 1 plus beta 2 plus beta nu. And I'm going to replace each of these betas now with the relevant expression from here. So I'm going to get, in other words, alpha nu is equal to alpha 1 plus alpha 2 minus alpha 1 plus alpha nu minus alpha nu minus 1. And then I'm going to take the limit of this. So the limit over nu of alpha nu is going to be equal to this thing. In fact, I'll tell you what, I'll write it like this. Limit over nu, and it's just going to add the rest of the terms in there. But this is just equal to beta 1 plus beta 2 plus beta 3 plus beta nu plus all of the betas added together. But I know all of the betas added together are just beta. So therefore this limit here is just equal to beta. The same beta that we were talking about up here. So this is for a fundamental series of ordinal numbers. I can talk about the limit ordinal number, which is from what we've shown here, it's a definite ordinal number. Not only that, it's the next greatest ordinal number after all of the terms of that fundamental series. So this is really useful now, because I've got if I start with an infinite, just a simply ordered series of ordinal numbers, I can guarantee that I can derive a fundamental series of ordinal numbers from that, and then I can guarantee that if I've got a fundamental series, that I can talk about its limit, and I know what the properties of that limit are. So this is a really important theorem, an important result that's going to be used time and time again throughout the rest of this work. So I've just got a few more little things that I need to go through before I finish this video, and then once I finish this video, we're going to move on in the next video to some more theorems. Okay, so the last couple of little theorems, not really theorems as such, but just properties of these ordinal numbers that I'm just going to go through now, just quickly. It's worth noting that this distributivity of ordinal numbers can be extended to these infinite sums of ordinal numbers. So now we just want to prove this and this. And it's not too difficult to do using the properties that we've already established. So if we start with this side here, the limit of gamma plus alpha nu, or if you remember, I'll just write it out one more time. The limit of alpha nu is equal to alpha 1 plus alpha 2 minus alpha 1 plus alpha nu plus 1 minus alpha nu plus etc. So this is what we understand as being the limit of alpha nu. So starting from the left hand side here, we get the limit of gamma plus alpha nu is equal to gamma plus alpha 1 plus gamma plus alpha 2 minus gamma plus alpha 1 plus, we're going to have to go down here, plus gamma plus alpha nu plus 1 minus gamma plus alpha nu plus etc. So remember, we've got an infinite number of terms in here, but using one of the properties that I proved earlier in the video, this here is just going to be equal to, this stays the same, this is just going to be equal to alpha 2 minus alpha 1. This is going to be equal to alpha nu plus 1 minus alpha nu. So now using associativity, I can say that this is going to be equal to gamma plus alpha 1 plus alpha 2 minus alpha 1 plus alpha nu plus 1 minus alpha nu. But this expression in here is exactly the expression that we've got here for the limits of alpha nu. So this is just going to be gamma plus limit of alpha nu, which is what we needed to show. And then moving over to this one now. Not really left myself enough space, but okay, again we're going to start on the left hand side. So we've got limit of gamma alpha nu is going to be equal to gamma alpha 1 plus gamma alpha 2 minus gamma alpha 1 plus gamma alpha nu plus 1 minus gamma alpha nu. Again, there's an infinite number of terms in there. Using now this distributivity, this is going to be gamma alpha 1 plus alpha 2, sorry, no, not just yet, a little bit careless. I've got to use a property that I proved earlier. Gamma alpha 2 minus gamma alpha 1 is going to be gamma alpha 2 minus alpha 1 plus gamma alpha nu plus 1 minus alpha nu, etc. Now I can use this distributivity to get gamma alpha 1 plus alpha 2 minus alpha 1 plus alpha nu plus 1 minus alpha nu, and this is equal to, in this set of brackets here, that's just what we've called limit alpha nu up here. So we get gamma times limit nu of alpha nu, which is exactly what we wanted to show. So that finishes up for this section. In the next section it's going to be much more theorem based. So I will be going through some of the theorems, not all of the theorems. So I want to thank you for watching this video, and I look forward to seeing you in the next video.